So today we're going to be talking through a new product that we just actually released last week. It's called the RAILGUN cookbook. And the purpose of the cookbook is to give developers a pretty easy way to structure smart contract calls so that they can fit within the sort of the RAILGUN system and allow you to transact privately with any smart contract call. And so we're calling these recipes, sort of, simple kind of housing for these calls. For example, you could do things with your private balance where you're staking tokens into vaults. This is something we're going to demo today. You could actually provide liquidity on Uniswap. You could do any variety of things, mint NFTs. You can do all of this stuff anonymously on Ethereum through RAILGUN. And Arbitrum, Polygon, etc. And so I know the title of the talk was about GMX, and we built a recipe for this, 80% of the way over the last few days. It's a bit difficult, and I'll kind of go into that at the end of the talk. We will have this recipe publicly available in the next week, but we ran into some challenges getting that out. So I'm going to demo something called Beefy, which is another vault mechanism. It's a way to store, vaults are essentially storing tokens, depositing tokens into a vault. You receive a vault token back, which is a ERC 4626. Typically with Beefy, it's a little bit different, but essentially that token can be redeemed for your original tokens that you deposited plus like interest. And so you sort of earn kind of a high interest savings account for your ERC20 tokens is what the purpose of a vault is. A lot of people, deposit tokens into a vault and they'll wait, they'll maybe redeem it after a year or something like that. They gain 5-6% yield on the tokens that they deposit. And through RAILGUN, you can do that entire process anonymously. So this appeals to like larger funds that might want to diversify their assets and gain interest on those, the assets they've accumulated. But they might not want to share those strategies with the wider community. They might want to keep that close to home. They had put a lot of money into research and all this kind of stuff. They don't want to share their alpha necessarily. And so that's where RAILGUN becomes essential. So there was a few other things I wanted to go over up front before we talk about like the exact code for the cookbook. So the way that the RAILGUN private balances work is through a zero knowledge system. So it's sort of, it's a system of smart contracts that lives on Ethereum, for example. You deposit tokens into that smart contract. We call that shielding. And then you can withdraw them at any time. We call that unshielding. And so that kind of process of going into the smart contract, it pools all the tokens together, but you have account level ownership of like your balance within this system. So rather than, like a traditional mixer style with sort of what I think of as like IOUs from the system that you can kind of cash in, it's actually like more like a traditional bank like checking account model where you actually have an account. It has a full history. You have account level ownership. You can share a viewing key to all of your balances and historical kind of transactions. You could share that with an auditor or your CPA or something. So it's account level ownership. When you go to make a private transaction, so, facilitating one of these recipe calls, a smart contract call to deposit in a vault, for example, it happens in 3 stages. So the recipe and the cookbook was really created to make this process very easy, where you really only have to worry about the second step, like the stuff that happens, the cross-contract call, and you don't really have to worry about like the housing and how it's facilitated within RAILGUN. What's actually happening behind the scenes is that you take your private balance and it will be unshielded into an intermediary contract. We call that the relay adapt contract. From there, something happens, right? You deposit into a vault, or you can do a series of steps. You can mint an NFT and assign it as an owner and do all this stuff that I'll describe for GMX later. It's a series of 6 or 7 steps. So it's an unshield, do a bunch of stuff, and then it takes whatever balance is left over after this series of steps, and it re-shields it into your private balance. This all happens without touching your public 0x account on Ethereum. And so this is how it's anonymized. It doesn't actually touch your balances. You won't see your account on Etherscan or one of the other block scanning sites. You're sort of out of the picture, and it's facilitated through smart contract logic. My screen died. And so what the cookbook does when you write a recipe, it's a series of steps that are kind of broken down, kind of bite-size steps. One, for example, could be like an ERC20 approval step, something that you usually do in a UI, right? You approve the token, and then you can swap on Uniswap or something. This can happen as a step, approve, and then, for example, that swap would be another step, right? And so those two steps become a two-step recipe. And that's facilitated. You don't have to worry about the unshield and shield, but that's how it will work on chain. So for Beefy, there's a few things to create a new recipe from scratch. So first off, you can follow along from Railgun community/cookbook. I'm not sure. Oh, there's the URL up there. This is just published last week. Our team's been hard at work getting this going. So cookbook is going to show, it's sort of how you create new steps and recipes. We call something a combo meal, which is multiple recipes kind of strung together, which we kind of find amusing. There's an integration test suite, which I'll demo as well. It's a little bit hard in this demo to write the full code for a step and recipe. It doesn't take all that long. It's just in a 30-minute condensed presentation. It's going to be a little bit of a challenge. And so I'm going to kind of just walk you through kind of the steps or the steps to creating a recipe and running that against an integration like fork tests. So the first thing would be for each of these new cross-contract calls, smart contract calls, the interfaces are called ABIs. People are probably familiar with those. When you deploy a contract to the Ethereum blockchain, the ABI is sort of the skeleton of the calls and of the events that happen that are available through the smart contract interface. And so the first thing you do here would be to add an ABI. Is this hard to see? I might bump it up. Here, how about that? So we've got Beefy here. We added the ABI. This came directly from Etherscan. So if you're finding one of the ABIs, you go to their contract. You can find their addresses through Beefy has decent documentation for this stuff. You can find their contracts over here. Go to Etherscan. In the contracts tab, you can find the ABI. You just basically copy and paste that. It's a structured array, JSON. Put that into a new file. And then we can go to create a Beefy wrapper contract. Where do we go? Contract. So the vault contract, let me get rid of these. The vault contract is very like a thin wrapper for the ABI. We generate types through something called type chain. This can take an ABI and generate TypeScript types for it. So we're using Ether's v5. There's a v6 which has nicer types like big int. But for example, I created a wrapper for these functions. The functions we're going to use from the Beefy vaults are deposit all and withdraw all, which is going to be for example, for they have like a curve convex vault, and they give you a curve convex vault token to represent that position. You can find the address of the Beefy vault for curve convex, construct new Beefy vault contract here, along with the address for this specific vault. They have hundreds of different vaults that they have access to, and they have a sort of wrapper contract that facilitates that shares the ABI between all of these vaults. and you can call deposit all to deposit your Curve Convex tokens from one account into the vault, and they will return you an appropriate amount of the vault tokens based on the current rate. So to know, the addresses of all the vaults, which vaults are available, Beefy does have an API. Their API is, it doesn't really have filters. Here's an example call. I just, like a GET call to this address will bring up a list of all the vaults. We wrote a quick wrapper around these things. So we have Beefy API just to find filtered Beefy vaults, so I can pass in to this function a list of tokens and then pull that GET request of 400 vaults and filter them by the tokens that I might have in my wallet. And so this returns the Beefy vault data. We have the ID, the vault name, which token address we're going to deposit, the vault token address that we get back, the vault rate, which is kind of constantly changing depending on how many people are depositing or redeeming from the vault, sort of like LP. There are fees on some of these. I think it's pretty rare, but these are pretty essential in calculating like what a user should expect, how many vault tokens they're going to get, which is pretty nice to see in a UI when you're building out these things. And they have an APY request as well, and the vault contract address right here. This is the piece I was talking about. So when we create a new Beefy vault contract that has the structured ABI, can access those functions, we're going to pass into the constructor, we're going to pass in the Beefy vault address that we got from their API. So this is really like the data request layer, and this is like, how do we format a smart contract call on Ethereum or Arbitrum, Polygon? They all work, all EVMs kind of have this structure. We can create a new vault contract through these functions. We can generate like two data and value fields, which is called a populated transaction. And this is kind of the format of any smart contract call. They have this, byte code, bytes of data to actually facilitate that call. And so we'll move to the next step. So this is really, we have our data, that's the API part. We have the structure of the call, and we have the contract to like generate one of these calls with a certain token. So we have like the basis right now. So the next part would be creating a step. I should say as well, this all of this code exists open source, as I showed on GitHub. It's also available as an NPM. So you don't necessarily have to like create a branch and like add code to the repo itself. You could download the NPM, create your own steps like offline, and facilitate against something called Railgun Quick Start, which will package those into calls against your private balance. So Beefy, I'm going to show here the Beefy deposit step. We have abstract classes for steps and recipes. If you were to create a new fresh step, delete the code in here, it'll tell you you're going to need a config, and you're going to need a function called get step output, which translates sort of the input values to this step into kind of filters what we expect the input to have. So I'll show right here, get valid input ERC20 amount. So we expect to have the token we're depositing in our balance at this point in the recipe, right? If we don't have the token we're trying to deposit in the vault, we're going to get an error when we call the contract. And so the cookbook kind of makes it easy, and it validates the actual inputs and outputs of each step along the way, make sure we have the tokens we expect. Of course, we don't actually know what the tokens will be if there's a logical error in the smart contract until we run it like on the actual contract, which is why we have integration tests, which I'll demo in a second. So we get the vault data from the vault ID. We have the token we're expecting to deposit. We make sure to get the from our list of inputs, we make sure that our deposit amount is there, and it will have a field called expected balance. From there, we create the new vault contract. This is what I was talking about earlier with the vault contract address, and we call create deposit all. That is the whole transaction that we're doing right here. The vault contract address is the important part because that'll tell us what is the token we're depositing, right? There's a different, as I said, different address for Curve Convex or all the other vaults. I have a wrapper util right here that kind of calculates fees and different things. So this is just kind of the math that's involved for estimating what the returned amount would be based on the vault rate and the fees associated to it. So this part is, for a given step, I said it has inputs, and we kind of translate those into outputs. Those outputs are going to be automatically verified, or validated by the mechanics of the recipe, which makes it like safe for users. When you're creating one of these recipes, it's harder to make bugs. You'll get error messages throughout the process. So for example, when we return the data from the step, there are these certain outputs that each step has in the recipe. A list of transactions, that's really important. That's what's actually getting called against the blockchain. Then we have a list of spent amounts, right? For example, we're going to spend the deposit amount, and we're going to gain the vault token. So we spend, and we have the output, which is the vault token, and associated fees, the deposit fee, for example, if there is one. These are the outputs from this step. And we have just kind of basic tests to make sure that when you create one of these steps and pass in certain inputs, that the outputs are valid for this step. Once you have a few steps, for example, with the deposit step, when we create a recipe, we're also going to need like the ERC20 approval step. It's the same kind of thing you would do. You approve the token before you swap. You have to do the same thing when you deposit into a vault. The ERC20 approval step is already created in the cookbook. Part of the impetus for making the cookbook in this kind of recipe step style format is that a lot of these steps are repeated. An approval will always have like a spender, like the contract that you're approving for. It always has a token, and it could have an amount or not. If you're, it's safer to approve with an amount, but you can approve the sort of max amount, which is pretty typical. And this step can be used in conjunction with any other like new steps that you create for a recipe, and so you won't have to like recreate the wheel here. When we look at the Beefy deposit recipe, the really interesting thing about sort of the format of this repo is that the steps have all that complicated math and the validation logic and all this like more complex stuff. But when you get to the recipe, the more abstract part of the cookbook, recipes are actually much simpler in code. Because they sort of use these complex steps and wire them together. The validation happens underneath. And so you can see actually the recipe is a lot less code. It's 45 lines total. It basically takes a vault ID. It's going to pull information about the vault, make sure that the network is supported. This is a required implementation within this class. And then get internal steps. So remember where I talked about kind of the three part process for a private call. There's the unshield, and then there's like the stuff, and then there's the shield. So internal steps is the stuff here. This is number 2, part 2. You don't have to worry about the unshield. You don't have to worry about the shield part. You just kind of name what the steps are. With the Beefy deposit recipe, we construct this with just a vault ID. So we do need a list of those from like the Beefy API ahead of time. For internal steps, we're going to pull the vault info, which is an API call with the vault ID. We're going to pull out the spender contract, which is which we're going to need for the approval step. We construct from the token address that the vault requires for the deposit and the amount of decimals, we construct kind of this info object about the deposit token. And then we return the two steps, right? We have an approval step for the spender and the deposit token. And then we create a Beefy deposit with the vault's data. And so the cool thing about this style, again, is like if you were to publish one of these recipes that has tests and all that, folks can download the code for that recipe. And when they're actually facilitating one of these pretty complicated private transactions, the code to initialize the recipe and pass in inputs is extremely simple. And it will tell them what the outputs are to expect. It'll have all the fees pre-calculated. They won't have to do very much, the end developers. Railgun is really like an infrastructure system. We're not necessarily going to be the ones that build the end products where people are actually, the wallets and this kind of stuff, where people are, facilitating the private transactions. We're building an infrastructure so that it's possible to more readily build applications with ZK privacy at the core. So I'm going to demo quick too. We have a special kind of test here that's for integrations or integration tests, which uses a system called Anvil by Foundry Up, Paradigm product. Anvil is similar to Hardhat or Ganache. You run an Anvil server locally, and it acts as like a virtual RPC. So it puts a RPC up on your local host, and you can actually fork the current state of Ethereum or Arbitrum and have that state sort of like delivered via your local host. So it's a really nice product to be able to test what is going to happen on Ethereum without actually paying gas to do all of those requests. So we have specific tests for fork mode. Just to look through this quickly, this test is for running the Beefy deposit recipe I was just talking through. For the recipe, we create or we pull the details for a vault. I have a specific vault, which I think is, the curve convex vault on Ethereum. I have a specific vault ID I have in mind already. I know what the vault token address is. So that's the information we're starting with. We're going to be on the Ethereum network. We have the vault ID already. We create, we pull the information from the vault, make sure that the expected information we get from the API is the same. We create the deposit recipe. This is the part I said, sort of the end product that adds like Beefy vault mechanic through this cookbook recipe. This code is pretty simple here. We pull in the deposit recipe. These are the inputs that are going to be originally unshielded from your private balance, right? When somebody goes into your UI, let's say as a wallet developer, and they want to deposit 1,000 DAI into one of these vaults, they select 1,000 DAI, and that's what gets passed into this recipe input. So for example, token address DAI, decimals would be 18, and the amount would be 1,000 or whatever it is. Let's see. So this is setting up initial values so that we can later expect that they've changed against the initial value. And this is it. Recipe output, deposit recipe dot get recipe output, and we put in, here's the expected input values. Recipe output is going to have a list of populated transactions. These are what are passed into a function in something called Railgun Quick Start, which is our wallet SDK. And this is how you actually call this recipe against the private balance. These populated transactions will contain all the data that's required. There is a wrapper here to actually run the recipe steps, like run the populated transaction against quick start and do all this stuff. It's in this wrapper here. And then there's some expectations at the end of this integration test. We want to expect that the private vault token balance has increased by the amount we expect. We in this recipe, we unshield convex curve, we deposit it into a vault, we receive convex curve vault tokens, and then we shield those back into our private balance. So at the very end of the test, we want to expect that that private balance has increased by this amount. I'll actually demo quick. We'll run this test. It takes a second to run because it has to run against the fork. I'm going to, we're on Arbitrum. Let's do scripts, run Anvil, Ethereum, and I'm going to put in Pocket, put in a public Ethereum address, RPC address for our fork. Oh, here, what's that? Run Anvil. Of course. Oh. So this is gonna, Anvil runs a lot faster than Hardhat, if you're familiar with that, or Ganache. Anvil, I think, is written with Rust. It is, when we switched over to it, it got a lot more performant. Now I'm gonna run yarn test fork. Actually, I might need, I can't remember, we changed this. Network name is Ethereum. And this is gonna run fork tests. We're going to see a little bit of an output here, which kind of describes what's happening behind the scenes. So fork tests, we can't guarantee that there is a balance in any Railgun account, especially one that we're going to put the seed phrase in integration test for. And so for this, we're using the like test junk seed phrase, which is a pretty common test keys for a wallet. It's going to load up the fork from Ethereum. It shields a bunch of initial tokens into this fork. The cool thing with Anvil is you can set it to pre-seed your test account with like 10,000 ETH, so you're never going to run out of gas. Right now, it's shielding tokens into my Railgun balance on Ethereum through this fork. And it's polling for the balances. So we can see the balances are found, and it's running this fork for the Beefy vault recipes. That is going to run the code we just went through to create the new recipe, to add in some inputs. Those are the tokens that are already shielded through this fork. The inputs are going to be validated against the expected output. It's going to actually run the call against the private balance. It's going to do all the stuff. It's going to deposit into the Beefy vault on this fork. Some error, great. During the demo, of course. The values are off by a small amount. They're off by literally, do you see what it is? One way. Some precision error somewhere. Yeah, there are some difficulties. For example, the swap recipe. So we use a 0x DEX aggregator, as you know, which pulls in prices from I think Uniswap and 1inch and all these different DEXs, and prices are constantly changing. And so one thing, there are a few limitations to like when you're building a recipe. Certain steps are designated as like non-deterministic. We don't know exactly what the amount will come out of it. But with, I think every recipe we've written so far, we limit you to having one non-deterministic step, because otherwise the calculations blow up and get crazy. But you'll have an expected balance and a minimum balance as the outputs of every step. And so, you know, with slippage or something, if your slippage is set to 1% on Uniswap, your expected balance could be 100, and the minimum balance will be 99. And if you wire a few of those together, again, it gets crazy. So it's a little hard to test, especially with these kind of precision errors. But I think when you build it as like certain steps and write unit tests for those, and then make a recipe and write unit tests for those, by the time you get to the integration tests, you've kind of ironed out most of those. The original, the code for these, like what I'm demoing, Beefy deposits, Kai, our protocol architect over there, and myself, we wrote this over about 12 hours last week on a single day. So it can be done. This stuff is like, once you get like in the flow of it, the whole purpose of this, again, is to make it easier than doing it from scratch. It's much easier as well having these existing steps and recipes as templates that you could copy paste and kind of fill in the own your details of your protocol. But it makes it easier to facilitate all of this. Time is it? I've got another 10 minutes. So any questions from y'all? I want to know what people want to know about. I know I talked for a while here. Go ahead. Oh, yeah. Yeah, I would agree with that. So the question was, what were some of the technical difficulties with GMX? I can actually show you, there's a few to-dos in this recipe, but let me see, GMX, stake, mint, GLP recipe. I won't go into the steps right now because those are, again, very complicated. The recipe looks a little simpler. But whereas the Beefy vault recipe was 2 steps, approve and then deposit, the GMX one is a bit more difficult. When we stake GLP token without necessarily having it, they have a contract call to like mint GLP and stake it. So you could provide DAI, for example. They mint you an equivalent amount of GLP based on the current price, and then they automatically stake that, and you earn yield on that staked position. The difficulty is that the owning account of that staked position is whoever called that function. In our example, that would be the relay adapt contract, and we can't designate that as like a private owner. And so we've designed actually a new system along with the folks at Gnosis Safe, where you can own a safe via an NFT. So you create a new safe, or actually we have you could do it in a variety of ways, but generate a new safe, assign it so that the owner of the safe is an NFT, and the safe itself acts as an account. So you can call the stake from the NFT-owned safe, and then you can deposit, you can shield the NFT into a private balance. The NFT owns the safe, which holds the tokens, but nobody knows who is the owner of the NFT. So that's what makes the whole thing private end to end. So you can see how it gets a little bit complicated. For this, so you can see the stages of this, right? We call it an access card, the NFT. This is kind of a nomenclature for, swiping your access card and you get access to the safe. So we mint an NFT. We create the NFT owner. This would be the safe, and then we assign the safe. We assign the NFT as its owner. We transfer the DAI to the safe because that's where it's going to actually stake from. It needs to be approved from the safe to spend against the GMX contract, and then we call GMX mint and stake from the NFT owned safe. After that, the NFT is sitting in the relay adapt contract, and it gets shielded into your private balance. So you'll hold an NFT that has ownership over these assets instead of actually holding those assets inside the RAILGUN contract. this is why this one would have been harder to demo, kind of the whole creating steps and things. It got a little out of control while we were writing this over the past couple of days.
Oh, 1 second.
So what's the problem that's solving? What's the reason that the relay adapter can't stake?
Well, the relay adapt, we certainly could call the stake from relay adapt, but then anybody at all could redeem it because it's owned by this sort of public utility. The relay adapt is what we think of as like a public utility. What makes it anonymous and private is that everybody's using it, right?
Okay, so there are some applications where you could do a kind of like atomic swap or something, and something could be owned by the relay contract, and other applications like this stake where there'd be no way to do it because there's nothing that's being swapped.
Yeah, so staking is an example of something that typically has like an owner address, and whoever called it, like if you look at the Solidity code on the smart contract, whoever called it, they just go, hey, take the address of that and like increment that value. They have a higher stake for that address. And so you can imagine if 3 separate people did it for the relay adapt contract, it would get incremented, and then somebody would unstake all of it. Do you know what I'm saying? And anybody would have access to do that because you can call anything from the relay adapt contract. It's sort of open-ended.
So like every stake position is basically non-fungible because the rewards accrue. Is that why? So I'm just thinking like, for instance, like an LSD, for instance, you can stake ETH, but it's just wrapped in an ERC20, so that's more fungible.
Yeah.
Like
So
could that maybe like also get around that?
So the difference, I guess, to clear it up, the difference with Beefy and why that one is much simpler is because when you stake or when you deposit into the Beefy vault, they issue you a token back. And some stake positions don't give you a token back, and some of them don't, right? They give you a representation of that stake, which you can privatize, which you can shield into your balance. But if they don't give you anything back, like is the case for GMX, they just kind of increment something on their smart contract and say, oh yeah, they've got something here, and they store it. Yeah. That's a situation where you need to store that somewhere. And we're getting around that through the NFT safe module. Sorry.
I got a question about the anonymity because as a depositor, let's say I want to do a swap on Uniswap. Mm-hmm. I deposit funds on the relay adapter. So that would mean there is a trace of my wallet going to the relay adapter, right? Then I do the swap. Let's say that I swap like 1 ETH back to 1,800 USDC.
Yeah.
At some point, that 1,800 USDC will leave the relay adapter back to my wallet. So, I mean, is it correct what I'm saying?
Yeah, absolutely. And so the whole thing is not end-to-end private in one of these relay adapt, what we call cross-contract calls, but it's fully anonymous. So full privacy would mean that the details of the transaction, the token amounts, et cetera, would be invisible. But you're right, because we're talking to another smart contract, liquidity pools on Uniswap, et cetera, those token values have to be known, right? You have to swap something, and somebody's earning those tokens, and that happens publicly. But it is anonymous. What happens in Railgun with your shielded balance, you sign or you generate a zero knowledge proof that validates that you have spend capabilities of a certain account within the system, right? That's what where the zero knowledge comes in. From there, that actually facilitates the unshield step that comes out from the Railgun core pool. Before it does relay adapt stuff, and that does happen publicly. You know the amount that came out of the Railgun pool, you know what swapped, you know what was deposited back in the pool, but because of zero knowledge, you don't know who the origin is, right? Or whose balance it came from within the Railgun contract. So let's say there's $1 million in the Railgun contract. You see 1,000 come out into RAILGUN and swap for wrapped ETH and go back into the Railgun balance. It was somebody that had a DAI balance, but you don't necessarily know who. And the fact that you can kind of swap in and out means that it could be like, it wasn't necessarily somebody that shielded it in. The other thing that's interesting is private transfers within the Railgun system are completely invisible, right? You won't see the value because it doesn't leave the system. It just sort of reassigns the owner within the system, which is interesting. And in the future, we will have capabilities to build like an atomic swap, like liquidity within the Railgun system, meaning that we could do swaps completely invisibly.
So that would mean that, let's say that I deposit with wallet A, I could take it out with wallet B?
Yeah, certainly.
So it's very similar to Tornado Cash. Are there like,
You could
I would
use it
imagine there would be some problems at some point.
Yeah, and we're doing a lot in terms of like compliance mechanisms. You know, kind of a non-KYC, zero knowledge way to prove that you are a good actor within the system. You can prove where the origin of the funds that you have unshielded to Binance or whatever came from a legitimate source and wasn't a sanctioned address or something else. So we're working on those kind of proofs right now that will hopefully make it more secure and safe for everybody to use these systems.
Okay, thank you.
Last question before lunch. Anything? Yeah. Okay. Thank you very much, John.
All right.
Great talk.
Thanks all.